Okay, Dr. Smith here, and what I'd like to do is talk a little bit about one of the problems on the WebAssign. You guys have a snow day, so nobody's going to be able to come in and ask me questions about this in person, so I want to just give you a little explanation of what's going on here. So the problem description says that this is the velocity of a star that's far away in the direction of the line of sight. And over time, so this is how it changes over time, and we're supposed to find out a couple things about the planet. I'm not going to tell you everything about the problem, but I'm going to give you sort of a hint as to what's going on. So you have a star, which I'm going to represent with a sort of dark orange dot, and that's going to orbit the center of mass of the system that it shares with its planet. That's bad. Let's see. I need a thicker pen. So, sorry, let's see. Oh, I don't want a pencil, that's why. Oh man, fun with free programs, eh? Is that a pen? That's pretty good. There we go. So, there's the center of mass of the system. And what the star does is it orbits. And so I'm going to draw where it is down there and then show it going in orbits around the center of mass. In reality, the star is probably going to be so big that the center mass of the system will include the star. But the star is there, and then at sort of opposite times, I'm going to show the planet as purple. Why not? The planet is out here and out here. So this is the planet, and now Lucy is up next to me, and she's sniffing at the stylus pen. So there's the star as S, the planet is P. And when the star is here, the planet is here, the center of mass of the system is here. This is just something, that we've been through. So you are way over on Earth, or we, or whoever is observing this is way over on Earth. And so this little symbol here is meant to be sort of an eye, and this is often used to represent points of view. And thank you, Lucy, for walking straight over the pad, but no damage done. So what can you see as you are looking from many light years away at this star? It does wobble a bit, but I think the wobble is the wobble this way, you can imagine seeing it sort of slide back and forth along your line of sight as it does this, but I think that's too small for us to detect with the telescopes we have. So we can't look at that, but what we can look at is the spectrum of light emitted by the star as it comes towards us and away from us. So the spectrum of the star, you've seen these things probably in chemistry where you have a spectrum of radiation going from, really low frequency stuff like cosmic waves and radio waves, and then I forget the exact sequence, but then you go through visible light, and then you go through ultraviolet into gamma rays and the super energetic stuff over here. And so different elements have different frequencies or characteristic wavelengths or frequencies for absorption lines. And so here's your spectrum, and if the star has a lot of hydrogen in it, then you might see a dark line at hydrogen, wherever that is. And so what happens is, as this thing is coming towards us over here, the Doppler effect causes the wavelength of the waves light waves coming from the star to shift. And I guess if it's coming towards us, the wavelengths get shorter. So what happens is that when it's coming towards us, so this is sort of the normal spectrum of the star at position 1, and now Lucy's coming back again. I think at position 1, don't quote me on this, but I think at position 1, the wavelength would be shorter. So I guess if you're doing higher, this is sort of the high frequency and low wavelength side of things. So when it's coming towards us, the frequency of the waves will appear higher. And when it's going away from us, as it is at position 2, the frequency will appear lower. And this is the Doppler effect. This is like the fact that the way that if a police car or an ambulance with a siren is coming towards you, the siren appears to have a higher pitch than if it is going away from you. And that's because the waves get compressed as they come towards you, so it sounds like a higher frequency wave. And as they go away, they become lower frequency. We'll study that. Oh, dang! I hate it when I do that. We'll study that when we get to waves. So now I have to somehow unrotate this thing. I hope. This is so. There we go. And then zoom it back up to 100% or so, and then recenter it. I'm sorry. And that's the frustrating thing for me, is that I can't undo that. So this is so touchy sometimes, this tablet. It's really great, but a little touchy sometimes. So this is sort of the neutral wavelength of, say, hydrogen. And so you would see this dark band across the spectrum of the star, because hydrogen is absorbing all the stuff at this wavelength. And so at 1, you would see this dark band shift this way, and that would tell you, that it's coming towards you. And at 2, you would see the dark band shift this way, which would tell you it's going away. And so you can, from these things, you can calculate the speed of the star, or the velocity of the star, in the direction of its line of sight. So it's kind of counterintuitive almost when we are actually looking at things physically that are far away. It's really easy to tell if they're moving sort of sideways across our line of sight, because we can just turn our head and see them moving, or our eyes have to turn to see them. You can see them move across what's behind them, etc. That's fine, and that's easy. But it's very hard for us to tell if it's moving slowly towards us or away, if it's far away, because you can't really detect the change in size as it does that. So this is kind of backwards from the way our intuition says it works, that we can see this movement much more easily than we could see this movement by the star. Anyhow, so let's see what's going on here. So here, the star is coming towards you. As it goes in this circle, the star is coming towards you. And this is where the component of its velocity coming towards you will be the maximum. When it's down here, the star is going this way, and it's not coming towards you or away from you. There's no radial velocity. It's called radial velocity because it's along the direction of a radius from your eye to the star. So anyway, at this point here, we have the maximum velocity is right there, or the maximum velocity towards you. And this is assuming you're defining coming towards you as positive velocity. Otherwise, it's backwards, but the math still comes out the same, of course. And then this down here is where it's going away from you at maximum velocity. So at this point, you have, from this plot, you have 2 pieces of data. You have what this velocity is for the star, and then you have the time between sort of the maximum velocities. So this time, I mean, you shouldn't have a hard time figuring this out now, that this time corresponds to, well, I've started the sentence, so I'll go ahead and finish it. It corresponds to the period of the star as it orbits the center of mass of the star and the planet, or the system center of mass. And then this here and this here correspond to the positive and negative, of the speed of the star as it goes around here. So here's the trick now. What you have to find for parts A and B are, I think A has you find the mass of the planet, and you have to do it in terms of Jupiter masses. That's just how these things typically get reported. They get reported as, scientists discovered a planet orbiting this star that has a mass 3 times Jupiter, or whatever. So that's why they want you to do it in Jupiter masses. And then part B is to find the radius of the planet's orbit, which is like that. So the planet, of course, then I'll stick to purple, but the planet then orbits in a circle sort of like that. Okay, so what you have to do now is figure these 2 things out from what you know about the star, that it was in a circle. You can find its speed, you're given that practically, and you find the period of the star moving in the circle. So 2 things to find, let's see. And what you're going to have to use is your Kepler's law stuff to find the radius of the planet's orbit, because now you know the period of the planet's orbit, and you are given the mass of the sun, or the star, sorry. You're given the mass of the star. So given that, you can find what the, let's see, should be able to find the radius of the orbit using Kepler's law, because you have period, right. So I guess what I'm going to tell you is look at B first, okay? B is easier. And this is the part that is kind of hand-wavy. You have to assume that, for part B, you have to assume that the mass of the star is much greater than the mass of the planet, which it is. And so what you should do to be doing this properly is, for part B, and I recommend doing that first, for part B, assume that the mass of the star, and that's what you're given, sorry, is much greater than the mass of the planet. And if you want to be really rigorous about this, so you can just do sort of the planet being in a circular orbit about a stationary point and the star just being there. And then for part A, you actually have to relax that assumption a little bit and say, okay, well, the star actually does move a little bit. And so it's kind of hand-wavy, because you're saying the star has this small circular orbit, the planet's is very big, and so really, compared to how far the planet is from the star's motion about the center of mass doesn't really change the gravitational pull, you know what I mean, compared to if the star were just here at the center. But then, for part A, which again I recommend you do second, you have to let the star be moving and and treat it that way. So it's kind of like, in one situation you make this assumption, and then for the other part you don't quite make that assumption. Okay, so for part B you assume this, and then you can find the radius of the planet's orbit, and from there then do part A. Okay, the trick for part A is there's a conservation law involved. It's not conservation of energy, it's not conservation of angular momentum, it's not conservation of mass. So think about the conservation laws we've learned and apply one of those to part A. And I've told you which ones it's not. You ought to be able to figure out which one it is. Not energy, not angular momentum, not mass. I've practically given it away already. So you apply that to find out basically what the mass of the planet must be, and, given the mass of the star and the other data you've got. Okay, I think if I talk anymore, I'm going to just end up giving away the problem, and I don't want to quite give this away for you. I want you guys to have to think about this a little. So that's my hint on that problem. So good luck.